Welcome to the video help with physics problems for Physics 1A. This video covers homework set 5, part 2, which is everything under the heading Heat Transfer. For 1121 students, this covers questions 3 to 6 and a past exam question. For 1131 students, this covers questions 4 to 7 and a past exam question. Problem 3 for 1121 or 4 for 1131. In this problem we have a skier. He's wearing clothes to insulate him from the cold. So the surface area of the skier is given by 1.8 meters squared. He has clothes with a thickness of 1.0 centimeters. His internal body temperature is equal to 33 degrees C, and the outside temperature is equal to 1.0 degrees C. The thermal conductivity of the material that makes up his clothes is given by 0.040 watts per meter per Kelvin. And the question asks us to calculate the rate at which heat flows through the clothing. So the equation that we need to use is that the rate of heat flow is equal to the thermal conductivity constant times the surface area times the absolute value of dt dx, where this is the temperature gradient across the surface and this is the width of the surface. Now all we need to do is substitute in the values. So we're told K is equal to 0.040. The A in meters squared is 1.8. The temperature gradient is 33 degrees on the inside and 1 degree on the outside, so we want a positive value, so 33 minus 1. And the thickness of the clothes, or the barrier, is 1 centimeter. We need that in meters as this is in meters squared and this is per meter. So we put 0.01. Entering that into the calculator, we get 230.4 watts. We should give it to two significant figures, so that's 230 watts. Okay, part B. Now the skier falls into water and his clothes become soaked. K changes as heat flows more readily through water. So the new K is 0.60 watts per meter per Kelvin. And so the new P, the only thing which will change will be this K. So we can do 230 over 0.040 times 0.60. Solving that on the calculator, we get 3,456 watts. So this is a lot larger, a lot more heat will flow through, which is why when you get wet, you get cold much faster. The other way to answer it is just to work out 0.6 over 0.04. That equals 15. So we can say that's 15 times the initial value. Either of those answers is fine. Problem 4 for 1121 or 5 for 1131. In this problem we've got two different scenarios. In scenario A, we've got a material with thermal conductivity K1 and a material with thermal conductivity K2 on two sheets, and we arrange them in a manner such that the heat flows through K1 and then K1 and K2 and then K2. In scenario B, we use exactly the same two materials, but we arrange them slightly differently. We let the heat flow through K2, and then after flowing through K2, it flows through K1. So possibly a better way to represent this is showing the side-on view. In scenario A, we have a hot side and a cold side, and we have the heat flowing through K1, then K1, and K2, then K2. In scenario B, we have a hot side and a cold side, but we have K2, then K1, and K1, then K2. We can let some temperature in the middle here, Tj, be the temperature of the junction. Now the question asks us, in which case would the rate of heat flow be the least? So each of these tiles has a surface area A. So this total surface area is 2A. Okay, let's consider some A first. Well, the power through A is given by K times the surface area dt over dx. So this is relatively easy to substitute in case A, because we'll get the power through this one and the power through this one, and all we need to do is add them together. So for A, the power through this top half with the K1s is given by K1. The surface area we're told is A. The change in temperature is the hot side minus the cold side. And the thickness, let's let each of these have thickness T. So this is over 2T. So that's how much heat flows through this top one. Now the bottom one, the difference with the bottom one is that we've got K2 here. So this is A, TH minus TC, the same thickness, so 2T. Okay, so let's just write this neatly. For PA, we've got A over 2T, TH minus TC, and then K1 plus K2. Okay, now we need to consider scenario B. In scenario B, the heat flows through K2 and then through K1. Now what we know is that the same amount of heat must flow from here to here as from in the middle to this end, because otherwise we'd have heat build up or loss in the middle, and that doesn't happen. The middle would then melt. So we have K2A TH minus TJ over T is equal to K1A TJ minus TC over T. These must be equal to avoid the build-up or the loss of heat from the middle. Okay, so A's cancel, T's cancel. What we're trying to actually do is get an expression for TJ, the temperature in the middle. So we can write this as K2TH minus K2TJ is equal to K1TJ minus K1TC. So putting all the TJs together, we've got the temperature of the junction is equal to K1 plus K2. K2TH plus K1TC, and so the temperature of the junction is equal to K2TH plus K1TC over K1 plus K2. Okay, we need some more space. So just recapping, because we'll need it, we had the rate of flow in case A was equal to A over 2T, little t, TH minus TC, K1 plus K2. And we just derived that the temperature at the junction between them, remember we've got K2, K1, K1, K2, TH, TJ, and TC was equal to K2TH plus K1TC over K1 plus K2. Now what we're trying to work out is the heat flow in this case. Now it doesn't matter, it's the same through the top half as through the bottom half. The order of the materials doesn't matter. As an exercise you can prove that, but it should be intuitively obvious. So the rate of heat flow in case B is 2 times what it is in this top case. Okay, so in this top case we've got that the rate of flow through here is the same as through there, so we only need one of them. So this is equal to K2, we're considering the rate of flow through here, A over T times the temperature difference which was the TH minus TJ. But instead of writing TJ, we'll write this expression here. So this is K2TH plus K1TC over K1 plus K2. Okay, so now we've got to make this neater. We can write this as 2K2A on little t, the thickness. And now what we need to do is put it all over a common denominator. So we've got K1 plus K2. And this is equal to THK1 plus THK2 minus K2TH, which will cancel, minus K1TC. Okay, now K1 is a common factor on the top, so we've got 2K1 K2A over T K1 plus K2. And then we've got TH minus TC. So that's our expression for the heat flow in case B. So let's write now, because we need to work out which one's bigger, PA or PB. Let's write PA over PB. Okay, so the A's will cancel out, the T's will cancel out. And what we're left with is PA is equal to, so the TH minus TC will also cancel out. K1 plus K2 on 2. And then PB on the bottom, we've got 2K1 K2 and K1 plus K2. So this is equal to K1 plus K2 squared over 4K1 K2. Okay, so now all we need to work out is this bigger or less than 1? Probably the easiest way to do that quickly is to let K1 equal 1, K2 equal 2. If these were the same, then we would expect to get 1 because there shouldn't be any difference between the two cases. So if K1's 1 and K2's 1, then this is 2 squared over 4, and this is 4 times 1 times 1. 4 over 4 is 1, so the rate of heat flow in both of them would be the same, which is good. But let's just work out which one's bigger when they're not equal. So when we substitute in, we've got 1 plus 2 all squared, so that's 9 over 4 times 1 times 2, which is 8. So that tells us that 8PA is equal to 9PB, which tells us that PA is greater than PB. So to have the least rate of flow of heat, we should choose situation B. Problem 5 for 1121 or problem 6 for 1131. In this problem we have a PV graph. We've got point I, the initial point, point F, the final point, and then we have a couple of ways of getting there. We can go through point A, or we can go through point B, and then we also have a path connecting the final point and the initial point. And we're told when the system is taken from I to F, along path IAF, so this way, then Q is equal to 50 joules. So it's useful just to write this on the diagram, and that the work is equal to minus 20 joules. And that if it's taken along path IBF, in this case, Q is equal to 36 joules. Okay, now part A asks us, what is the work done along path IBF? Well, I and F are fixed states, so we know that the change in internal energy is the same between these two states no matter which path we take. And the change in internal energy is equal to Q plus W. So we know that QIAF plus WIAF is equal to QIBF plus WIBF. And so we have 50 minus 20 is equal to 36 plus WIBF. Rearranging this to get WIBF, we have this as 30 So 30 minus 36, that's minus 6.0 joules, giving it to two significant figures. So let's just add that to this diagram. W is equal to minus 6.0 joules. Okay, part B. If W is 13 joules for the curved path F to I, so here W is equal to 13 joules, what is Q for this path? So we need to find Q. Okay, now we knew that the change in internal energy going IAF or IBF was equal to, well, this one or this one. Let's do this one. So this one's 50 minus 20, so 30 joules. So the change in internal energy going this way is 30 joules. So the change in internal energy going this way, so delta E int from F to I is equal to minus 30 joules. This is from I to F, so they have the opposite sign. Okay, now we can just use the first law of thermodynamics again. So this is equal to QFI plus WFI. We're told the work is equal to 13. So the change in heat is equal to minus 43 joules. 43 joules of heat flows out. So Q is equal to minus 43. Let's write that along that path so that we have a record of it. Okay, part C says take the internal energy at point I to be 10 joules. Okay, so E int is equal to 10 joules. And what is the internal energy at F? Well, we know from going from the I to F, we increase the internal energy by 30 joules. That's what this told us here. So this is equal to 10 plus 30, which gives us 40. So the E internal at F is equal to 40 joules. That's the answer to part C. Okay, part D says if the internal energy at B is 22 joules, find Q for the process I to B. So this Q is for the entire path. It's from I to B to F. We now need to find Q along this path and Q along this path. Well, let's start with this point going from B to F. The final internal energy here is 40. The initial here is 22. So the change in internal energy is equal to 40 minus 22, which gives us 18 joules. Now the work done going from here to here, there's no change in volume, so work is equal to 0, which first law of thermodynamics then tells us that the change in internal energy is equal to W plus Q. So that tells us that Q must be 18 joules. So Q from B to F was equal to 18 joules. And we know that the heat flow going from I to B to F was equal to 36 joules. So that tells us that the heat flowing in going from I to B is equal to 36 minus 18, which is equal to 18 joules. And so that has answered everything that's been asked of us in that question. Problem 6 for 1121 or 7 for 1131. In this problem, we have a piston pushing down on a mixture of water and steam. Here's our piston. The area of the piston is given by 2.0 centimeters squared. The mass of the piston is equal to 2.0 kilograms. This piston is pushed down at a rate of 0.30 centimeters per second, which will be changing the volume. The density of the steam inside the chamber is given by 6.0 times 10 to minus 4 grams per centimeter cubed. And the atmospheric pressure is equal to 1 atmosphere. Now part A asks us to calculate the rate of condensation of steam. Well, the amount of steam, the mass of steam, is given by the density times the volume. So the rate of condensation, the change in the mass of the steam with time, is equal to the density times the change in volume with time. Okay, so the change in the mass of the steam is given by 6.0 times 10 to the minus 4 grams per centimetre cubed. Now the volume is equal to the area, so that's the 2.0 centimetres squared, and the change in the height with time is 0.30 centimetres per second. So solving this on the calculator, we can see all these centimetres will cancel out, so we'll end up with an answer in grams per second. Entering that into the calculator, we get 3.6 times 10 to the minus 4 grams per second. So we're making the assumption that the density of the steam in there remains constant. Part B says, at what rate is heat leaving the chamber? Well, heat is generated by the change in state of the steam. The formula to work out the heat is mass times the latent heat of, in this case, vaporization, but we want a rate, so let's just divide it by T. So this will be the change in mass with time, which is what we've got here. So we can just substitute in. We've got 3.6 times 10 to the minus 4 grams each second is being created, and the latent heat is 2.26 times 10 to the 6. Now this is joules per kilogram, so let's convert this into kilograms. So we've got another 10 to the minus 3 there. So this is per second again. So this is equal to 0.8136. So to two significant figures, that's 0.81 joules per second. Now, this answer is a little bit dodgy because we used this value, our standard value for the latent heat of vaporization. This value is measured at atmospheric pressure, but the pressure inside here, we've got the atmospheric pressure, but we've also got the pressure coming about because of the force of this acting on it. So that's force over area, which is mg over A. So m is 2 kilograms times 9.8 divided by the 2 centimeters squared. When we do that on the calculator, we end up with 98,000, which is around about 1 atmosphere. So instead of being 1 atmosphere in here, the pressure is around about 2 atmospheres, which means that this is actually a little bit different. If you look up this value for 2 atmospheres and substitute it in, you end up getting a slightly lower value here. But this is a reasonable approximation. Okay, part C. What is the rate of change of internal energy of the steam and water inside the chamber? Well, the change in internal energy comes about because of two things, because of the heat and because of the work. Okay, so we want rates, so let's just divide everything by T. This is just the first law of thermodynamics. Now, up here, we calculated this term, so this one's done. So what we need to do is work out the work. So work is equal to the integral of P dot dV. So in this case, this is P times dV dt, how the volume is changing with time. So the pressure inside, like we've noted over here, is equal to P naught plus F over A, which is mg over A. Now we have to times it by the volume, which is the surface area, times the height, except that we're doing how the height changes with time to get a rate. So that's times the 0.30 centimeters per second. Okay, so substituting in, we've got 1.0 times 10 to the 5 plus 2 times 9.8 over 2 times 10 to the minus 4 times 2 times 10 to the minus 4 times, and now this volume's decreasing. We should have our negative sign here, and this one here is negative as well. So those two negatives actually cancel each other out. So we've got 0.0030 meters per second. solving that on the calculator, we end up with 0.120 joules per second. Okay, so we've got 0.120, and now this Q, this heat is actually flowing out. So for the change in internal energy, this is going to be a negative heat. So this is equal to minus 0.81 plus 0.12. Doing that on the calculator, we end up with minus 0.69 joules per second. So that's the rate of change of internal energy with time. It's a bit of a mess, sorry about that. Past exam question. This is part A of the 1131, or the entire question for 1121. So in this question, we have a flask. There's an external pressure PA, the atmospheric pressure, and initially we have a volume V0 in this flask. Then we put on a piston. With mass M and surface area A, which applies a pressure, and this comes to a new equilibrium height. H0, and it also comes to equilibrium temperature T0. So initially it's at T0, and it comes to some equilibrium temperature T0 again. And we're asked to derive an expression for H0. And we're told that the air inside, we can consider it to be an ideal gas with a molar mass of 0.029 kilograms per kilomole. Okay, so if we have an ideal gas inside, we can use the ideal gas equation. PV is equal to nRT. Now, the number of moles is not changing. The R is a gas constant, and just before the piston's put on, it's in thermal equilibrium at a temperature T0, and after the piston's put on, it comes back to that same equilibrium constant. So this whole thing here is a constant, and so we have PV is equal to a constant. So what we have is PA, the atmospheric pressure, times the initial volume, V0, is equal to the new pressure. Now the pressure inside here, we've got the atmospheric pressure acting still, but we've also got a force acting, and pressure is equal to force over the area. And so the force acting is the mg, the weight force, over the area A. So that's the new pressure, and then we've got a new volume. It's at height H0 now, but it's still got surface area A. Okay, so what we need to do is rearrange this for H0. So we've got H0 is equal to PA V0. Now there's this A, and then we're dividing by this as well. So this is 1 over PA plus mg over A. Okay, let's multiply the A in here. So we've got PA V0, PA A plus mg. Okay, so that's probably as simple as we can give it. So that is our answer for the equilibrium height. For 1131, there's a part B. So part B for 1131 only. Okay, now we're told that this acts as a suspension system with a stiffness equal to the ratio of the force on the displacement. Okay, so it's displacing it's starting at some height h, and then it's dropping down a bit to a height h minus x. So this is at pressure, say P, and this is at pressure P dash, some higher pressure. Now it says, would the system be stiffer for a rapid displacement or a slower one? So let's divide this in half and look at the two cases. Okay, so slow implies isothermal. Always has time to come to equilibrium with its surroundings. Rapid implies adiabatic, as there isn't time for heat to flow. So here we have PV is constant, and here we have PV to the gamma is constant. Okay, so we've started from this volume. This is A, so the volume is AH, and the volume here is AH minus X. Okay, so in this case we have PAH is equal to P dash, the new pressure, times AH minus X. These will cancel, and we end up with the change in pressure, P dash minus P, is equal to, well, P dash is equal to PH over H minus X, and then we've got minus this P here. So this is equal to, taking P out as a common factor, we've got H over H minus X minus 1. So this is equal to P, let's put it all over a common factor, H minus X. We've got H minus H plus X. That's just multiplying this by this. So these cancel. And so we've got Px. Now X is small, so H minus X is approximately H. And so the change in pressure, which is equal to the force over the area, is equal to Px over H, which tells us that F over X is approximately equal to Pa on H. So that's for the isothermal case. This gives us the stiffness constant. Now for the adiabatic case, we've got PAH to the gamma is equal to P dash H minus X to the gamma A to the gamma. Our A's cancel out again. And so our change in pressure, P dash minus P, is equal to, in this case, P dash is equal to PH to the gamma over H minus X to the gamma. And then we have to minus off this P again. Okay, so let's take P out as a common factor. Now we've got H to the gamma over H minus X to the gamma minus 1. So let's just rewrite this as P. Let's switch this the other way up. So we've got H minus X over H, and that's to the minus gamma minus 1. And so this is equal to P. Now this is 1 minus X over H to the minus gamma minus 1. Okay, so we can do a binomial expansion of this. So this is approximately equal to 1 minus, now the next term is minus X H times minus gamma. So we can make that a plus. And then we've got this minus 1 term here. We won't include any more terms because X on H is small. And so when they're higher order, we can ignore them. Those will cancel. And we've got, this is P gamma X on H. Now we do the same thing as here. The change in pressure is equal to the force over the area, which is approximately equal to P gamma X on H. And so we've got F on X is approximately equal to P gamma A over H. Okay, so this is different from this one by the factor of gamma. So this one's stiffer. The stiffness constant is higher. So the rapid one is the stiffer one.